We've all seen what modern AI can do, right? It's incredible. It can write code, create amazing art. It really feels like magic. But here's the thing. What if I told you that all that genius is actually, well, surprisingly fragile? Let's get into it.
And I'm not kidding. This is a really serious question. Because underneath all that power, there's this hidden weakness, a vulnerability to something called adversarial attacks. And listen, these aren't your typical software bugs. Nope. This is a deep, fundamental flaw that could totally shake our trust in these systems. So what are we even talking about here? What's an adversarial attack? Well, picture this. Someone takes an image, say a photo of a stop sign, and they just tweak a few pixels, just a handful, so few that you and we wouldn't see a thing. The sign would still look like a stop sign to us. But to an AI, that same image could suddenly look like a speed limit 100 sign. And the scary part? This isn't random noise. It's a carefully crafted, targeted attack designed to fool the system. And that right there, that brings us to a really important point. The fact that these attacks even work tells us something huge. It's not just a security patch we're missing. It points to a much deeper issue with how these AI models are actually learning about the world. I mean, really think about that for a second. If an AI can be fooled that easily, does it really understand the concept of a stop sign? Or did it just memorize some superficial patterns? And you can see why this matters so much, right? When we're talking about self-driving cars or AI diagnosing diseases, a small mistake could be catastrophic. The difference between getting it right most of the time and being truly robust, well, that's everything. Okay, so how do we fix this? Researchers figured out that just patching for one attack at a time was like playing a game of whack-a-mole. It was never going to work. They needed a whole new way of thinking. So they reframed the problem. They started treating it like a strategic game, an epic battle between an attacker and a defender. And this right here, this is a huge shift in mindset. You see, normal AI training, it's all about minimizing the average mistake. It's like trying to get a B+ on a test. You do pretty well overall, but robust optimization, that's totally different. The goal there is to minimize the worst possible mistake. It's like preparing for a test where your worst enemy gets to write the questions specifically to make you fail. You're not aiming for a good average anymore. You're trying to make sure you don't get a 0 no matter what. This whole idea gets formalized into something called a saddle point problem. Now that sounds super technical, I know, but the concept is actually pretty straightforward. It's a min-max game. First, the max part. You unleash an attacker whose only job is to find the one tweak that maximizes the model's error. Then, the min part. Our defender, the model, has to adjust itself to minimize that worst-case error. It's this constant push and pull, this tug-of-war during training that forges a stronger model. Right, so if we're going to train our defender this way, it has to face the toughest opponent imaginable, A fortress is only as strong as the cannons trying to knock it down. So the big question becomes, how do we create the ultimate attacker? And the answer to that is something called projected gradient descent, or PGD for short. Now this isn't just a one-and-done kind of attack. It's smarter, it's iterative. Think of it like a heat-seeking missile. It takes a small step, looks at the model's own weaknesses, what we call the gradient, and uses that to figure out the next most damaging step to take. It does this over and over. And that's why it's considered a universal adversary. It's pretty much the strongest attack you can possibly make, if all you know is the immediate direction of failure. And man, is it effective. Just look at this graph. What you're seeing is the model's error just skyrocketing in only a few steps of the attack. It shoots up and then flatlines at a super high level of failure. This isn't a fluke. It shows that PGD is brutally efficient at finding a model's pressure points, and it does it fast. And what the researchers found, which is so important, is that it's incredibly consistent. It doesn't matter where you start the attack from. PGD almost always finds its way to a point of maximum damage. And that reliability, that's exactly what you want in a training partner. It makes it the perfect sparring partner to build a truly tough AI. Okay, so we've got our game plan, a min-max training setup. And we've got our ultimate opponent, PGD. But there's one more piece to this puzzle. And honestly, it's kind of the opposite of what you might expect. Turns out, to make these models more secure, you have to make them bigger, a lot bigger. So why is that? To get it, we need to talk about something called a decision boundary. Think of it like a line in the sand the AI draws to separate, say, cats from dogs. A normal model, it draws a really simple, efficient line. The problem is, an adversarial attack just needs to give the data a tiny nudge to push it over that simple line. Boom, your cat is now a dog. But a robust model, it can't do that.
It has to learn to draw this incredibly complex, wiggly boundary. It's like building a giant fortified wall with a moat around every single data point. And here's the kicker. Building that fortress takes a ton of resources. A small, simple model just doesn't have the horsepower. It literally lacks the complexity, the capacity to draw such a complicated defensive line. But a big model, one with lots of capacity, it has the flexibility and power to do it. Think of it this way. PGD training gives the model the blueprints for the fortress, but it's the model's capacity that provides the stone and steel to actually build it.
And you don't have to take my word for it. The data is crystal clear. Check out this graph. On the bottom, you have model size, its capacity, and going up the side is its accuracy when it's under attack. And that brown line, that's our PGD trained model. Just look at that curve. As the model gets bigger, its ability to withstand these attacks goes through the roof. This is the evidence right here. Capacity isn't just a nice to have, it's absolutely essential.
So what if you ignore this and try to use a small model? Well, it's a disaster. It just doesn't have what it takes to learn that complex defense. When you force it to try, it gets confused. It has to make a choice. Either be robust against attacks or be accurate on normal data. It can't do both. It's a trade-off it's doomed to lose because it's just not big enough for the job.
All right, so the theory sounds solid, right? You take a big model, you train it in this attacker-defender game against PGD. But does it actually hold up in the real world? Let's check out the results.
So here's some data from the classic MNIS dataset, the one with handwritten numbers. On regular images, no attacks, the model is nearly perfect, 98.8% accuracy. Great. But get this, even when hit with a white box PGD attack, and that means the attacker knows everything about the model, every single secret, it still holds up at 89.3% accuracy. That is seriously impressive. Okay, that's great for an attack it's been training against, but what about a surprise attack, one it's never seen before? What if the attacker doesn't have the blueprints? That's the real test of a good defense, isn't it? And the answer is a huge yes. The model is also incredibly good at fending off so-called black box attacks. This is where an attacker creates a weapon on a totally different model and then tries to use it on ours. The fact that our model can defend against that, it proves it's not just memorizing answers to one test. It has learned a deep, fundamental type of security. This chart really puts it all together. You see that first bar? That's a standard model. Attacks transfer to it super easily, it's very vulnerable. Now look at the next ones. Once you add PGD training, that transferability drops. But when you have both PGD training and a big model, the transferability basically disappears. The two pieces working together create this amazing generalized defense. So when you boil it all down, the secret sauce for robust AI seems to have two key ingredients. Step 1, adversarial training. You have to train it against the strongest possible opponent, and right now, that's PGD. Step 2, you've got to use a neural network that's big enough, that has enough capacity to actually learn the complicated moves it needs to defend itself. So it's become pretty clear that if we want AI we can actually trust, making it accurate isn't enough. It has to be robust. And what this research shows us is that robustness isn't free. It costs us in terms of bigger models and more complicated training. So as these AI systems get woven into the fabric of our lives, the real question we have to ask ourselves is, what's the price we're willing to pay for systems that are not just smart, but also secure,